Welcome back. We are now going to reach the zenith of this difficulty curve. It's sort of a chi-square, so it's going to tail out very nicely. By the last block, you're going to think, oh, this is easy. So we're going to leave you with that feeling for today. But then tomorrow, it's another matter. All right, so this is a slide where Morten ended. He ended with formulas representing what he showed in pictures. And really, this is the essence of learning this area. Looking at formulas like this, means of 4 different kinds. And the way to look at them is really to read the, it's almost like reading the subscripts. Here you have 1, 0, 0, 0. Here you have 1, 1, 1, 1, 1, 0. So how do you read that? Well, if you look at so there's so many levels that you can understand this on. Now I'm going to show you the most shallow level. And, you know, that could be enough for a person like me, for instance. So you have here 1, 0, 0, 0. So if you look at that, the M0 is the same, right? In both places. What does that say? That's the notation for how M varies under the control condition. Now what the first number is the value of X. This is treatment, X is treatment, this is X is control. So we let M vary as it would under control condition. That's the normative distribution for M. The way M would vary if there was no treatment. But then you say, okay, we compare the treatment here with the control here, while holding M at values that appear when you have no treatment. So you block off the treatment part. The effect cannot go through the treatment. So it's a direct effect comparing treatment with control. So 1, 0, 0, 0 is that. Now we're going to focus more on the indirect effect up at the top. And it's maybe a little bit harder to see how to read that. But if you look at it in a very simplistic way again, now the first index does not change. You're considering treatment for both of them, but what changes is the M. M varies as it would under treatment, and M varies as it would under control. So here you're no longer blocking off the mediated effect. So you let a mediated effect be compared to a non-mediated part. So it's an indirect effect. At this point, all you have to do is look at the indices. If the second varies, then we're probably talking about an indirect effect. If the first varies, we're probably talking about the direct effect. Now, if you dig a little bit deeper, what Morten was talking about was the case of continuous M, continuous Y. And he did not specify functional form. He did not specify linear regression like I do here. But let's talk about these quantities that he talked about in this simple case. And once again, we have to remember what the definition is. What does this construction mean? And this you will see in the causal effect literature quite a lot. It refers to the variable y when x equals x1, say treatment, and the variable m varies as it naturally would when x is equal to control, say. So that naturally varying idea is why the term natural indirect effect comes about. Now the total effect, that has 1, 1 compared to 0, 0. So that's this is the treatment group mean. M varies as it would under treatment, and we are considering a person under treatment. And this is X is control, and M varies under control. So it is the control group mean. So you can say this is a treatment group mean minus control group mean. That's a simple total effect, right? Now the total natural indirect effect, if we get back to that we looked at in the previous slide, you have 1, 1, 1, 0. 1, 1 is easy to understand. It's the mean of y when subjects get the treatment, and m varies as it would under the treatment condition. This is the treatment group mean again, just like we set up here. But here's the counterfactual that's a little more involved. The mean of y when subjects get the treatment, but m varies as it would under the control condition. So m varies as under the control condition. This is a counterfactual. What we're doing here is blocking off any effect of x on y via m, because m varies as it would under the control condition. So it's blocked off. So what's left then is, when we block off that effect via m, what's left is the direct effect part from x to y, and that's what we subtract from this effect. And therefore, since we subtract off the direct effect part, we get the indirect effect. That's the reasoning. Now, that may or may not make life any easier for you, but this is how it applies to the simple continuous linear m and y case. Now, let's take another look at this, and we'll get back to the continuous case in a while. Let's get back to the hypothetical example with a binary m, so no longer continuous m. And we showed you this picture, right? And we agreed where the squares should be in the picture, and we looked at the 4 means here. And now we're going to focus a little bit more on the distributions of m under control and under treatment. So here's a slide that tells you a lot of the story. And once again, it's easier to demonstrate this in the binary m case than it is in the continuous m case, but we're going to do both. So first of all, assume that m equals 1 is the more desirable outcome for m than m equals 0. And assume that a high value of y is more desirable than a low value. So for instance, if we look at the control group here, x equals 0, that's a normative behavior, normative distributions. So the probability for m, say that that's 0.67 for m equals 0, and 0.33 for m equals 1. Those were the values that we got out of this figure, right? 0.67, 0.33. That's a distribution of m under the control. And in the control case, we have y for m equals 0 and y for m equals 1. And we notice then that m equals 1 is the better mediator value, more desirable value, in order to get the high desirable y mean, in this case, y bar. Now, so that's this part here. X equals 1 increases the probability of, well, okay, no, it's not. Now we're comparing these two. That comparison for m, so the treatment group effect here is to shift the distribution to have more m equals 1 than m equals 0 as compared to this distribution. So the treatment moves m into be more likely for m equals 1 than what it was for control. All right? So that's the m1 is more desirable, and we influence m being 1 by x being 1. And now we also see that m equals 1 increases the mean of y relative to m equals 0. And that's true both control group and even more so for the treatment group here. So we have an effect of x on m and an effect of m on y. And one critical idea here is that we have two distributions for m. This is the distribution for m in the control group. Much more likely to have m equals 0 than m equals 1. And the reverse in the treatment group, much more likely to have m equals 1. So these are two distributions. Now, what we're after is to look for the mean of y given x. But we have, so that's two variables related to each other. But we have three variables to begin with. We have x, m, and y. What we want to do is collapse over M, get rid of M. Later on, we're going to use the term integrate out M. So we want to only relate y to x. We want to forget about M. So what we do then, if you look at the bottom here, this is the treatment group mean. So x is in the, x has the value 1, and M varies as it does on the 1. Let's see, where do we have that? So we're looking for a mean of 9 here for, this is the x equals 1 for M equals 0. And so you can scribble here. This is the x equals 1, M equals 0 mean. And this is the x equals 1, M equals 1 mean. You can compare to this, you just write down these two. And what we do is we weight that over the distribution of M, which has probability 0.33, 0.67. Which ones did we take? We took this distribution. We didn't take that one. Because this is M varying as a function of, as it varies when x equals 1. So up there you could say M parenthesis 1 here. So that's the distribution of M under the treatment. And up here you can scribble M parenthesis 0. So we're using the M distribution for treatment, 0.33, 0.67. You see that these change over the 4 different parts here, which distribution we work with. Now, that one, those two bottom ones, they relate to the indirect effect. So what is this? How is that constructed? Well, it's the same means, 9 and 12.5, as you have down here. But now you're considering the distribution of M in the control group. So you use 67 and 33 as the weights. This is the collapsing over over M rather. Collapsing over M to get the mean of y for a certain value of x. So there you have that counterfactual again, That's the 1, 0 term, which you looked at up here. The 1, 0 term, the counterfactual, whereas this is the very easily understandable treatment group mean term. So you have the treatment group mean, it's a real event, and you have the counterfactual. I'm just looking at 2 of the 4 here to point to the indirect effect. This is clearly something you want to sit down with in an easy chair and work your way through. But anyway, the key is that you collapse over M. Collapsing means that you just sum over the different possibilities of M. You go from x to y. You go either via M equals 0, M equals 1, 2 paths, and then you weigh them together to come to y. I can see many more figures coming in the next version of this course. But anyway, so you collapse over M. In the binary M case, that's a weighted sum, like you see here. And the trick is that this is the M distribution for the treatment group, and this is the M distribution for the control group. So the weights are different. Anyway, so you get these means. You actually get 4 means. We're not going to focus on the first 2. And the indirect effect is that mean minus that mean. All of these values come from the table you have here. All of the data is here. We use these things at the bottom line here. And here you get it. Here are the counterfactually defined effects for this hypothetical example. And here's the definition of the acronyms: T total, E effect, N natural, I indirect, D direct, P pure. Different authors have different versions of this, but this covers it pretty well. So what is the indirect effect? Well, now you just read those numbers. 1, 1, 1, 0. That's the indirect, right? 1, 1, 1, 0. That's the total natural indirect effect. That is the indirect effect. Those two numbers, 11.33 minus 10.17, 1.17 is the indirect effect. Total effect is given up here. That's 1100. Pure natural direct effect 1, 0. You know, you have the 1, 0, 0, 0. So 1 changes, but the M0 does not change. And that turns out to be 1.17 as well. As it says then here, also you have the total effect is equal to the total natural indirect effect plus the pure natural direct effect. You can check that in the numbers, down to rounding errors. The relationship between m and y may be different for the two x values. So that's the m and x interaction effect on y, right? Interaction between m and x and their influence on y. This is what creates a difference between total natural indirect effect and pure natural indirect effect. Total natural and pure. That difference is 0.67, right? 0.67. Which says that the exposure-mediator interaction contributes more than half of the total natural indirect effect. So 0.67 is more than half of 1.17. So it's a fairly strong interaction between exposure and mediator here, which can be quite hard to see in the original data. Maybe you are sharper than I in reasoning about seeing that. But it's a strong MX interaction in this case. And that gets shown as a difference between the total and the pure indirect effects. And as in Morton's example, the estimation is non-parametric, not assuming linear or logistic regression. We just did the multiplication and addition, and then we didn't introduce a model anywhere. All right. Now are you ready for the continuous M case? Binary M case is actually simpler. So now you can do binary mediator modeling with continuous Y all by yourself by hand. You don't need, I shouldn't say that, but you don't need the Mplus for that. So now we go back to Morton's case of a continuous M, and we focus still on the indirect effect, so 1, 1, 1, 0. In the continuous M case, you can't sum over two binary values of M because they're not binary. So to collapse, we instead integrate. That's the continuous version of summing over those two M points, 0 and 1. So M has two different distributions once again. M equals 0 for x equals 0, and M equals 1 for x equals 1. So this term, this critical term 1, 0, you know, the second part, the counterfactual part of the indirect effect, is then an integral. So you get to draw this beautiful sigmoid shape which goes integrate from minus infinity to plus infinity over, you integrate out M is what that says. And you take the expectation of y given x and m, particular m value, multiplied by the distribution of m. This f is a distribution of m. And typically then in the standard linear mediation case, that's a normal distribution. Distribution of m given x is normal. In some cases, this integral is simple, and you don't need to do it. You wouldn't have to show it at all, and that's the case for continuous m, continuous y. I don't need to do this integration. And also for continuous m and binary y with probit, you don't need to do the integration. In some cases, integration is needed. Continuous m, binary y with logistic instead of probit. But then that integration can be done very nicely by so-called numerical integration. So numerical analysis handling of integration. You don't have to know an explicit form for this result. You do a sum over many terms. And also for these examples we're going to show later on today, count and log y outcomes, you need that integration. But let's take a look at the continuous case again. This is a simple case, right? Y linearly regressed on m and x. M regressed linearly on x. Now let's first take the integration approach and then show that's the same as a simple approach where you don't have to integrate. And once again, the critical term that we always focus on is the 1, 0, the second part of the indirect effect. So what you do is you insert m into this equation, put it in there. So then you have beta 0 plus beta 2x plus beta 1 times m, right? Beta 1 times, and the m part, that's where m appears. That's where we want to integrate out m over the distribution of m given x. The distribution of m given x at x equals 0, so x0 comes in there, whereas x1 comes in here. So x1 comes into the first equation, and x0 comes into the second equation. What's in this rectangle here, by definition, this expression, m times the distribution of m, integrated out over m, is the expectation, the mean of m. So that's a simple formula that tells you it's the mean of m. And what's the mean of m given x? Well, that's gamma 0 plus gamma 1x. The mean of the residual is 0. So the mean of m is here. Mean of m given x at the point of x0 comes in here. And collecting terms, you have beta 0, beta 2x, beta 1 times what that turned out to be, namely the mean of m given x. So integration is a general approach, but not needed here. If you just consider x equals x1 in 34 and x equals x0 in 35, and insert the mediator expression in the outcome expression, put mi in there, we get the same result. Beta 0 plus beta 2 x1 plus beta 1 times this. I'm just saying that this is the general approach. You want to have a general approach, but you also will be happy when it simplifies. But you want to know what the general approach is. Okay, so that's the 1,0 term. So then if you go to the next slide, we have not only the 1,0 term for to get the indirect effect, but we have the 1,1 term. What's the 1,1? Well, first of all, here is the 1,0 term once again. You see that? x1 for that and x0 there. This is just like on the previous page. What the 1,1 is, you put in 1 in the first equation, in the y equation, and you put in 1 in the second m equation as well. And then you look at the difference between the two. The book is full of these examples, and it's ridiculously simple. You see then that you get rid of beta 0, you get rid of beta 2 times x1, subtract 1 from the other. Out comes the standard simple beta 1 times gamma 1. The regular A times B effect comes out there. So terms cancel out, and the indirect effect, as usual, is the product of two slopes. In the simple case of no interaction and m and y continues. This does not hold for binary y, but now we know how we handle the general case, because we have gotten general knowledge always applicable. So now you take a deep breath, and now we put the binary distribution on y. Binary y still continues m. It would have been easier with binary m and binary y, but we're going to do this. This case is probably the most common case of those that deviate from the standard continuous m, continuous y. So we're giving those of you who love formulas their moment here. So, okay, so we have then, we see a y star here, and now the newfound knowledge that we got from this morning, we see that that's an expression for, say, probit regression. That's this continuous latent response variable behind the binary observed y. And in probit, that would then have a normal distribution with fixed variance 1 because it cannot be identified. But otherwise, it's a standard y regression on n on x. And then you have the regular m equation, where in that case m is observed continuous. So now we condition on x equals x1 in the first equation and x equals x0 in the second equation, and insert m into 38 into 37, and look at the mean of y star given x. That's mean of y star given x. And you get beta 0 plus beta 1 times, that's the beta 1 times gamma 0, gamma 1x, and it should be x0, plus beta 2x, which is x1. And then, in this case, you also have to take into account the variance of y given x. What's the variance of y? What varies in y star, rather, once we condition on x? Well, the only thing left are these terms, right? But when we insert m in there, you have beta 1 times this epsilon plus that epsilon. So you have the variance of beta 1 times epsilon sub m plus epsilon sub y. the variance of that sum, since those two are independent, we can't identify that correlation, remember, is beta 1 squared times the variance of m plus the variance of this, which I call C. In probability regression, C is 1. In logistic regression, I misspoke earlier. The residual variance, C is pi to the power of 2 divided by 3. Did I get that right? Thank you. Okay, so it's a constant. So now to get the probability of y equals 1 given x, standard statistics says that's phi, the normal distribution function for the mean of y given x divided by the standard deviation of y given x. A standard deviation of y given x is the square root of this thing. So you see that, and then the naturally indirect effect is using again the 1, 1, 1, 0 that we talked about all day long, except now we do it using the normal distribution function, a very nonlinear S-shaped function. So 1, 1 uses this term, and 1, 0 uses that term. And you see then that this model, all of its 6 parameters, 1, 2, 3, 4, 5, and variance 6, are involved. All 6 parameters are involved in these effects. So obviously it would not be sufficient to just take A times B or gamma 1 times beta 1. All 6 are involved. So in the book we describe a little bit more back and forth intuitively why that would be the case, why A and B is not sufficient. So all 6 parameters are involved. I went through this also because there's an article on our website using a two mediator case, and a person from around here, I think, Hopkins, did an article on that in the DSEM journal, generalizing this. But it's the same basic idea. This is the crux. You have to take into account this conditional residual variance. Anyway, enough for the formula lovers. We can also express effects on here. The effect is expressed on a probability scale. These phi values are ranging between 0 and 1. So it's in probability metric. So the natural effect increases or decreases the probability of y being 1. Now you can do it in odds ratio instead. You recognize, this is the natural indirect effect again, in odds ratio form. You recognize the 1, 1, 1, 0. So you take the odds, the probability 1, 1 divided by 1 minus that, that's the odds. And then the odds for the 1, 0 in the denominator. And the ratio becomes an odds ratio. And you don't need to have logistic regression for odds ratios. It's just that with logistic regression they simplify. But you have this expressed in a phi probit form, where the probit argument here is what we talked about down here. All right. Now, Van der Weel and Van Steeland showed in an article that with logistic regression, the T9 odds ratio that we just talked about, this one, with the logistic regression, it's approximately equal to this, e to the power of an expression that looks very much like the usual indirect effect expression, beta times gamma, and then moderated term as well. So it's an indirect effect formula except exponentiated, e to the power of that. And when the treatment is continuous, you have the continuous difference between x1 and x2. But that's when the outcome y is rare, so like 5% or something. Probability y equals 1 is like 5% or 10% maybe even. Then you can estimate beta 1 and beta 3 and just exponentiate, and gamma, and exponentiate them to get the indirect effect odds ratio. And Morten's going to show you how well that approximation works. So here you have it. This is a very nice, I think it was a Psychological Methods article by Valerie and Van der Weel. And you may want to read it through for a second and really savor the words. The important thing that you want to underline is it is important to note that randomizing the treatment is not enough to rule out confounding issues in mediation analysis. This is because randomization of the treatment rules out the problem of treatment outcome and treatment mediator confounding, but does not guarantee that the assumption of no confounding of mediator outcome relationship holds. So the randomization does not help for the mediator outcome relationship. Because treatment is randomized, the mediator is not. So in the causal effect literature, you see a lot of discussion about the various assumptions. And I'm not going to focus on that here now. In our book, I reacted against the counterfactual literature talking so much about causal effects. I'm always skeptical when people say that this is a causal effect. So just because you use counterfactual definitions, which are rigorous, doesn't mean that the result is any more causal if the assumptions don't hold. So this is what I wrote, so you may want to read that. So on a positive note, one can claim that it's better to use effects under some well-defined circumstances or causal, even if in a particular application one is not sure if the assumptions are fulfilled. Strength of the counterfactual provides a roadmap. Because if you don't define the effects in a way that's reasonable under some assumptions, then you don't know what you have. And with that, I think it's time for a little bit of applications. And now the chi-square curve starts sloping down again.
Finally, right?
Yeah.
All right, so now we're going to look at some examples of non-standard or non-classical mediation analysis. And it's really nothing to it now when we let Mplus handle all the problems for us. So we have this example now where we have a binary outcome variable, which is cigarette use, if you use cigarettes or not. We have a treatment variable trying to reduce the cigarette use. So this is a intervention program for grade 6 and 7 students in Kansas City schools. So they gave this intervention, tried to decrease the proportion that used cigarettes. And as a mediator, they measured the intent. So 6 months after the intervention, they measured the intent to use cigarettes during the following 2 months. And then they measured the cig use as if they've used cigarettes during the last month, which was after these 2 months. And the observed cigarette use of the whole sample was 80% in the end. So I just want to say here then that since this is now a binary variable, we cannot longer just take the product of these two, like Bengt said. We cannot longer take just gamma 1 times beta 1. So now what should we do then in Mplus to not make that mistake? First of all, the total effect, as Bengt showed, can be computed even without doing any mediation analysis. That would just be the difference of the proportion of smokers or cigarette users in the treatment group or in the treated group and in the non-treated group. So in this case, 14.8% of the people in the individuals in the treated group used cigarettes in the end, whereas 22.4% in the non-treated group was using cigarettes in the end. So that's the total effect. If we don't take into account whether or not we could change their intent, we just look at if the treatment worked or not. So the difference there is minus 0.076, so 7.6%. And you could of course also look at the same outcome in the odds ratio scale, where we just take the ratio of the odds. And both of these then indicate the same thing, that actually taking this treatment reduce the probability of using cigarettes, since this is smaller than 1. Okay, so let's see how we can set this up then. Well, it's very similar to the mediation models we looked at before. But as I said, if we have an outcome variable, a dependent variable that is not normal and continuous, we have to specify what it is. And in this case, the outcome variable sig use is a binary variable. So we have to say categorical equals sig use. And that's pretty much it. The rest is exactly like we did before. We use the maximum likelihood estimator, and we use the probit link in this case. And since we use the maximum likelihood estimator, we want to use the bootstrap to capture the non-symmetric confidence interval, the skewness of the sampling distribution. So we use the bootstrap confidence interval here. And then in the model indirect command, in this case, we don't have any moderation, right? We go back to the model. We don't have any moderation in this model. maybe we should think about adding it, but let's just say for the sake of the argument that we tried it, but it didn't change any of the effects. So we use the ind option for indirect effects. So we use the outcome, and we don't have to say anything again about that this is a binary variable now because we have specified that. So we just go ahead as usual and say siguse ind, and then the mediator, and then the exposure. And we don't have any values in parentheses after the exposure, and that's just because it's a binary treatment, right? So we'll see the shift from 0 to 1 by default. So we don't have to specify that. And here are the effects for this model. This is actually the confidence interval output. So in the confidence interval output of Mplus, you have the effects here, and you have the estimate in the middle, and the lower percentiles to the left and the upper percentiles to the right. So this value and this value is the 95% confidence interval for this point estimate. And this is the total natural indirect effect in this case. So this, remember now that these are not symmetric, these confidence intervals, because they're based on the bootstrap confidence interval. And as you can see here, we have a significant indirect effect, which is minus 0.02. And it's significant because the confidence interval does not cover 0 here, right? So both are on the negative side. And the direct effect is not significant because the confidence interval covers 0 if we are at the 5% level. And of course, you could also look at the odds ratio for the same effects, where you would have the point estimate 0.85, and the confidence interval does not cover 1 in this case, so it's also significant. And usually, the probability scale and the odds ratio scale should agree on if it's significant or not. If they don't agree for some reason, then you should be very skeptical about the results. All right, so this is pretty much what I said. This is just the explicit interpretations of the effect here. The final bullet here, though, I want to mention. So the total effect can be compared now to the proportion of cigarette users in the control group. So in the control group, there were 22.4% cigarette users in the end. So we kind of think about it as that is the proportion that would have smoked if no one was given the treatment, right? So the question is, of the people who were smoking, how much could we reduce that? So how large is minus 0.02 or 7.2% as compared to the 22.4% that were actually smoking? So that would be a 32% drop. So of the people that smoke, we could reduce that number by 32% if we would give them the treatment.
So this wasn't a randomized control group?
Yeah, it was a
Yes.
randomized trial.
It was a randomized control group, but it had 22.4% of people who had smoked? Or
No, this is only the group of people that didn't get the treatment.
didn't get it?
Yeah, so that's our,
Your control group had 22.4% of people who smoked?
yeah, in the end. So the total sample had 18%, and that was made up of the treated group that had 14 point something percent, and the non-treated group that had 22.4%.
But
Or
in the
20.
control group at the beginning, what was the percentage of whoever smokers?
We didn't measure that. There's no baseline measure in this case, right? Not included in this model, at least.
Okay.
Yeah. All right, so the second alternative here would be to use the rare outcome assumption that Bengt was talking about. So let's see how well this approximation that Van der Weel and Vansteland showed, how well it works, right? So we could do it then in both ways. We could use, and like Bengt said, then that would be kind of going back to the classical effect, but just take the exponent of them. And I will show you exactly how. So we will do actually both here. We will both specify the counterfactual-based causal effect with the model indirect command, like we just saw. We will also, in the model constraint command, calculate this approximation. So since this derivation of this approximation is based on the logit link, we will use the logit link also in this example just to stick to that. But it probably wouldn't matter as much if we used probit or logit here because they're very similar actually if you look at the outputs. So the way we do it is that in the model command, we give the slopes labels like we talked about in the first example. So we say that the slope of siguse on intent should be named beta 1, on TX should be named beta 2, and then the intent on the treatment should be given the slope gamma. And then in the model constraint, we can call these then. We have these labels on them. So we can say we want to create 2 new coefficients here, 2 new parameters. Indirect, which is the indirect effect, which is then the exponent. So exp is a built-in function for an exponent in the model constraint command. And then just the product of these two. and the direct effect is simply the exponent of beta 2, corresponding to these names. So now we can compare these two results and see how well the approximation works in this case. So the first one is not assuming a rare outcome, so the model indirect based effect, which on the odds ratio scale, we already seen that, is the point estimate for the indirect effect was 0.85, and the direct effect was 0.716. So if we compare that then to the rare outcome assumption, we see that it's close, but not exactly the same, which you would expect. It's an approximation. So in this case, the rare outcome result indicate a stronger effect. However, first of all, the rare outcome assumption may not be suitable in this case because there's only 18% of the total sample that uses cigarettes, so it's not that rare. And also, it's an approximation, of course. So we shouldn't choose between the results here based on which one has the strongest effect. And when I say the strongest effect, I mean that 85 is closer to 1 than 84, you know, because 1 would be the odds ratio correspondence to 0 effect. So we should, of course, choose, if we want to use this approximation, we should base that on that we have a rare outcome. And like I said, probit and logit regression here gives very similar results for the probabilities. And with that, I think Frank will step in and take one example.
All right. Thanks. So this is an interesting example because it has many complications. And maybe start with the picture here first. You have the slides next to each other so you can see. So this has to do with being vaccinated or not for the HPV rather. And here you have an intent to vaccinate mediator, and you have, in this case, several treatment variables. We're going to focus on the treatment variable called TX2. And we're going to take a look at the model that has an interaction between this treatment and the mediator. So we have that MX. So maybe you want to bold that square, that we focus on that, and bold this square, MX. The MX then influences the binary outcome. That is, the regression of this Y on M is moderated by X. So, and here you have a set of control variables: communication, age, sexual activities, and knowledge about HPV. So you should think about this. Maybe you want to scribble. This is the case 3 moderation. Case 3 moderation you want to scribble up here. You have the description of the sample more on the previous slide more carefully. Here's a typo. If you want to be precise, it should say 2.09 instead of that. And here we talk about the total intervention effect and probability metric, 0.10. That's an increase in the vaccination rate. And then the odds ratio metric is 2.70. So now we want to divide up this total sample estimated total intervention effect into direct and indirect effect. So in this case then, this is an M times X case, right? And that was the case 3, as we said. That was the most complex case where the effect depended on everything, basically. It depended on the X values that you choose to compare. It depended on the control variable values. And the effects depend on the control variable values for 2 reasons in this case, actually. Because it's case 3, where even in the continuous Y, the effects would depend on the control variable values. But we also have a binary Y, and we agreed that then all of the parameters of the model, and also including the C values, affect the indirect and direct effects. So now I get to be applied and talk about Mplus input for a second. Morten shouldn't have all the fun. So we have categorical vaccination, and Mplus figures out that that's a binary variable. And we define M times X as intent by the mediator times the treatment variable tx2. And just for fun or for simplicity, we center both age and knowledge so that those variables will have 0 mean. And we use bootstrapping in this ML context. And we have the two regressions, y on m and all of the x's and c's, and m on the x and the c variables. And then we use the model indirect version for the mx interaction that you have on at the bottom of your cheat sheet. We can never remember which slide it was, but you'll find it. So you have the vaccinations moderated intent for mediator mx moderation interaction, and then the binary treatment dummy variable. So that's pretty simple input, right? But you have to remember what you're getting here and how to interpret it. So here it comes. So vaccination on intent 4, that's a logistic regression, right? How do we know that? Is it a logistic regression? Yeah, we say it is, so it should be. And we have estimator equals ML, where the default for ML is logistic. So if you don't say link equals probit, you get logistic. So this is a logistic regression, and we see that y on m essentially is significant. It's greater than 1.96. Look at the p-value there. Once again, the mx interaction is non-significant. That doesn't go above 1.96. M on tx2 is significant, thank the Lord. At least we have that. And the rest, I guess, is not that interesting. So we get to this. So here, in the output, you should search for confidence intervals of all of the effects based on counterfactuals, causally defined effects. For your enjoyment, we've also included the classic interpretation, classic effects like A times B. And we call that the latent variable derived effects, where that's really the effect for y star, not for y. Y star is linear regressed on m, and m is linear regressed on x. So there you can use A times B, that is beta times gamma. But that's not the effect for y, and we're talking about the effect on y here. So you look for counterfactuals, and then again, as Morten said, you locate the estimate in the middle column here, and the lower and upper confidence intervals for the 95% non-symmetric interval based on bootstrap. So these are the bootstrap percentiles here. So you see then that because the lower and upper limits are both positive, they are bounded away from 0, we can say that there is a significant positive effect in the increase of probability of vaccination of about 5%. And whereas the direct effect is not significant, these intervals include 0, so that's not significant. Total effect is significant, and that's how big it is. And you can look at it in odds ratios as well. Now this is without intervention-mediator interaction. What we really showed in the picture is the with intervention-mediator interaction. And you saw that that interaction was not significant, but nevertheless, it plays a role. This indirect effect estimate gets increased here when you have the intervention-mediator interaction. So, but whereas the direct effect is still insignificant. And also the odds ratios increase from 1.448 to 1.541. This is further away from 1, so it's a bigger effect. So having letting the intervention variable interact with the mediator gives you results that you probably will be happier with. So even though the interaction wasn't significant. The sample size here, what was it? 394, which is still a little bit too low to find perhaps significant interaction effects. Here is the bootstrap distribution for the indirect effect in probability metric. You have the point estimate here, 0.05, which is what we talked about before, what we have down here. And you have the upper and lower limits, and it looks skewed, so it paid off to use bootstrapping, because bootstrapping allows skewness in this indirect effect distribution, and allows therefore the 95% interval to be so-called non-symmetric. That is, this distance from the mean or median here to the lower limit is smaller than this distance. And that's motivated by the fact that you have this skewed tail here. So this is a non-symmetric distribution for that. Deep breath for introducing a count y instead of a binary y. So now we're getting into what we talked about this morning, count modeling again. And as you remember, we have then distribution of rare events, probabilities tapering off very quickly, probability of being at count 0, 1, 2, etc. And we had a log rate or log mean equation that was linear like this. For extra emphasis, we have an m times x interaction here, and we have control variables here. And then you have the mediator equation. And just like before, we take the general approach, that's always correct. Counterfactually based causal effect, consider terms such as, here we have the 1, 0 term again, and by now you recognize that as the counterfactual situation, the second term in the indirect effect definition. And again, its general case is an integration over m, where that integration becomes a little bit more complex. It goes through several lines of derivations in the book, taking into account that the rate e of y, which is the rate, is actually the exponentiation of that equation, which complicates things a little bit, but not much. Anyway, that is the approach that we take for count outcomes. And here comes, what was your name again? Coming back for application.
All right. So now we're going to look at actually the example that we started with this morning, but in a bit more elaborate way. So we have again this randomized field experiment about the aggressive disruptive behaviors of elementary school students here in Baltimore, actually. So now we have the treatment variable that we had this morning, so an intervention trying to reduce the aggressive disruptive behavior. We have the baseline aggression, so the aggression in grade 1. But now we're not going to look at AG5 as the final outcome, but the mediator. So we say we measure the aggression in grade 5, and then the outcome variable is now the number of times you've been removed from school during these years. So it's a count outcome. It's the number of times. There's 250 individuals in this study. And as you can see, we now use the interaction between the intervention and the mediator, so n times x here. And of course, you could think about other interactions as well, the one we talked about this morning, so the interaction between the baseline aggression and the treatment. So there's a lot you could do here, but let's look at this example for now. So the way to set it up, I feel like I'm repeating myself, but the way to set it up, if you don't have a continuous normal outcome variable, you have to specify what you have. And now we have a count outcome variable. So remove is a count variable. And we can think about using the default Poisson if we think that the assumption about the equal mean and variance would hold. But in this case, it turns out that the negative binomial one, allowing for dispersion, the dispersion parameter, fits the data better. So we're going to use that one, the negative binomial distribution. And then in the center option here, we center both AG1 and AG5, but for different reasons. So AG5 is a part of the interaction. So we want to center that to make the interpretations easier. AG1 is not part of, it's not a mediator and it's not a moderator. So why do we want to center that one? Well, that has to do with how these effects in the model indirect command are calculated. And they're always evaluated at the value 0 for covariates. So since AG1, if we go back to this, AG1 is just a covariate in the regression of AG5, and it's just a covariate in the regression of remove. So this will be evaluated at the value 0 of ag1. And if 0 is not a meaningful value, we can center the variable, and the effects will be evaluated at the mean of ag1 instead, which makes more sense in this case.
Can you just remove your outlier? Instead of random mean centering, can you just remove your outlier? Like if it's a collective variable.
That wouldn't help this interpretation, though. This would still be
In general, can you just remove your outlier?
of course, you can remove outliers, but that's, I mean, yeah.
Yeah.
Now that would probably be the first thing I would look at, outliers and distributions, and see if you have floor effects and stuff like that. And then since we have we have moderation, so we just write it on this form. We have the outcome variable. Again, we don't have to mention anything that it's a count variable. We've already done that. So we just say remove and then mod, the mediator ag5, and then straight to the interaction variable mx, and then finally tx. And again, tx is a binary exposure, so we don't have to specify any values within parentheses afterwards. We will see the shift from 0 to 1. And these are the confidence interval estimates for this one. So again, these are based on Bootstrap now. I'm kind of taking that as a default now, because we'll always use that with the maximum likelihood estimator. So now we have the point estimate here, minus 0.119. It's a significant effect. So it's difficult to interpret. We're going to work on that soon. But it's a significant effect, a significant negative effect. We have the direct effect, which is non-significant because the confidence interval covers 0. And I just want to mention here, it says other effects. And these are, as Bengt said, you can decompose the total effect in different ways. So usually we will be interested in the upper ones here. These will be the primary interest usually. But you can sometimes be interested in these, and I just want to mention them because they are in the output, so you might think about what they are. And you can read about it in the book. I think it's equation 4.14. Maybe I should look before I say that. Yeah, 4.14, equation 4.14. So just so you know what they are. But usually we're happy to interpret these. We're going to do that now. So as I said, so this would be the bootstrap distribution, then, like Bengt said. This is based on the 10,000 samples that we made, bootstrap samples or iterations. And we can see here that the non-symmetric confidence interval does not cover 0. We have a significant negative effect. However, the point estimate of minus 0.119 is not very easy to interpret. It's on the log rate scale, right? So what does that mean? It lowers the probability of school removal somehow, but it's hard to interpret. So again, we're going to use kind of the trick of looking at the specific outcome. Remember when we compared the two-part model and the censored models that were on different metrics? We looked at the probability of a 0 count for a specific group. So we're going to do a similar thing here to have some kind of interpretation. How does this intervention affect the probability of a 0 school removal? So we're going to look at that. So essentially, the intervention increases the probability of a 0 school removal from 29.4% to 43.5%. You can turn that around and say that the probability of not being removed from school increases with 14% units if you're given the treatment, as opposed to if you're not given the treatment. So you have a higher probability of never being removed from school, 14% higher, 14% units higher. Yeah. All right, so I just want to look briefly into what about if we have a two-part outcome for the mediation model. I'm going to go through this a bit briefly. I just want to recap the two-part modeling and the two-part data command. So what we did was that we had a variable that has this peak of, say, zeros, for example. And we create one binary variable coding for if you're larger than 0 or if you're at 0. So binary, so it's equal to 1 if you're not at the floor, not at 0. And then we have the positive part, which was the logarithm of the original value, if you had a value larger than 0. So in this case, we're going to use a probability regression to describe the probability of being at larger than 0. Yeah. So we will have this 3 regressions now. We will have the logarithm of the original value if you have a value larger than 0. So if u is equal to 1, that will be a linear model like this. So we will have the mediator, linear model like this, and then the probit model for the probability of having a value larger than 0. So now we come back to this example. So it's the economic stress data, which Bengt already showed you once, but I'll remind you. So what we have here is an exposure variable that is economic stress, how stressed you are about your economic situation. And this is small business owners that are in the sample. So how stressed you are about your economic situation, and the mediator is a variable representing how depressed you are or how much negative emotions you have. And finally, the outcome variable is a continuous variable representing thoughts about withdrawing from your entrepreneurship. So thoughts about withdrawing from your business and instead become an employed person, so you don't have to think about this economic stress. And if you look at the outcome variable then, which is how much you think about, and this, remember this was a combination of 3 7-point scales, something variables. So we have a big peak here at 1 in this case, which is the lowest value. So a lot of these individuals, 30%, had very few or none thoughts about withdrawing from their entrepreneurship. But then we have a distribution here. It actually looks kind of normal, but then we have this tail here. So in this case, it makes perfect sense to use the logarithm to pull this tail up and make this even more normal resembling. So this is kind of a perfect variable for two-part modeling. So how do we set this up then? Well, this is a bit more complicated. We start by using the data two-part command. And actually first we rescale, or we shift the withdraw variable, so we have the point, the peak at 0 instead. So we just take -1 to move this down to 0. It doesn't matter for the interpretation where we are. So when the cut point is at 0 then instead. And we create, from the variable withdraw, we create one binary variable that we call u, and one continuous variable that we call y. And again, the continuous is now the logarithm of the original variable. And we have to tell Mplus that u is a categorical variable. And then we put up our model here. Now the question is, how can we get the correct indirect and direct effect for this model? We have an outcome variable that is a two-part variable. It has one binary part and one continuous part. And what we could do is try to do one part. So we could take, for example, the binary part and we have no moderation here, so we could just take the binary part and say u, ind, and then the mediator, and then the exposure here. And now you see that we have values in parentheses after the exposure, so we have to choose for what shift in the economic stress we want to see the effects for. And in this case, it's from the mean to one standard deviation above the mean in the E stress, in the economic stress. But this is not the complete indirect and direct effects for this model. We have a two-part outcome, so we should essentially derive the effect for a two-part outcome with the counterfactual-based causal effect. And this can be done. You can derive these effects and get analytic solutions to that. So now I'm going to show you how you can implement this in the model constraint. And this might be intimidating at first, but maybe after a while also, I don't know. But the point here is that the indirect and the direct effects, or the expected values that I was talking about before, the 4 expected values that we need to find, they are always a function of the parameter estimates. So we can always just give names to all the parameters in the models, all of the parameters that we need to use. And if we can derive and find analytic solutions to these 4 expected values, we can implement them by hand in the model constraint command. So what you see...
This is the stuff we try to shield away from you, so you don't see it. It's behind the scenes usually, but here you see it actually.
Yeah, so I just want to mention that. So what we do here is essentially, you see these 4, E, Y, M, and these 4 of them. These are the expected values. We have 4 expected values here. So just above the bolded syntax here, you have the 4 expected values. So we have one explicit solution or one explicit expression here for each of these expected values. And then the total natural indirect effect and the pure natural direct effect is just functions of these, right? We just subtract them from each other. So the point of this slide is not to show you how much syntax, I guess, Bengt can write. The point is that you can, with this definition, you can define the correct causal effects for any kind of model. So if you can find an analytic expression, you can implement them by hand. So you kind of have this tool that always kind of will work if you have this explicit solution.
So we can Bowling call y star y hat. Would that be y? Would that
questions for the question and answer session, please?
Yeah. All right. I think that was Yeah, okay, so let's compare then what conclusions we'd have drawn if we would have used different kind of outputs. So the first one is if we treat it as a two-part outcome and we use the effects that we so smoothly just implemented in the model constraint. So these are the kind of the correct effects if we believe that the two-part outcome is the correct outcome for this variable. So we would have then the point estimate is 0.20 here. And if we compare that then to looking only at the binary part of the two-part model with the model constraint like we did in the syntax, we would have another effect, 0.07. And if we look at the indirect effect for only the continuous part of the two-part variable, we'd have 0.11. And if we just don't care about that we have this peak at 0 and just look at the original variable, but take the log of the original variable, just log transformation of the original variable, we would have 0.18. And if we would use the original, we would have 0.89. So they're very similar in some sense in this case, but that's not always the case. They could also be very different. But in this case, they kind of tell the same story. Actually, everyone is significant in this case. But if we believe that the two-part outcome is the correct one, then we should, of course, use that. And in this case, this effect is larger. It's a larger effect if we treat it as a two-part outcome than if you don't. So I think, do you have anything to add, Bengt?
I just want to talk about the next slides.
Thank you. I just want to emphasize what Morten said and do it in the context of that vaccination example I talked about. So on slide 114, you have the control variables down here where the HPV communication is a binary variable, age is continuous, sex discussion is binary, knowledge is continuous. So we have two continuous variables, age and knowledge, and the other ones are binary. And these are C variables. You want to perhaps circle it and call them the C variables. Now, what I did here was to center the continuous variables. Like Morten said, the effects are evaluated for control variables at 0. So since the mean of age and knowledge is not 0, we subtract the mean from them. So they have variables. So they have mean 0. And therefore, the effects will be evaluated at the age and knowledge means. And at the 0 alternative for the rest of the binary C variables. Now, if you want another value for the C variables, you can just rescale the variable and change it so you get it. For instance, if you want it for another binary variable, you just change the order of 0 and 1 in the binary variable and get that effect. So it's always evaluated conditional on C equals 0. So you have to keep that in mind. And in fact, some people might want not effects conditional on specific C values, but unconditional over C. So in that case, you would have to get the effect for each C value in the sample and then average all of those effects yourself. That maybe is a feature that we want to add in the future once you fall in love with these kinds of effects. So that's what I want to say about that. Now, there's a lot more to mediation analysis than what we have been able to cover here. In the book, we also talk about the case of an ordinal M and Y, and talk about using either the observed M or the latent response variable M for a binary Y, for instance. And we also talk about the nominal M case, which has come up a couple of times on Mplus discussion, nominal Y, which can be handled, as the book describes, using mixture modeling with known class can be done. What is not in the book, except for a sentence, is a binary outcome with multiple mediators. In fact, everything in the book for counterfactually defined effects is for a single mediator. It is a complex case to go from single to multiple mediators in the sense of providing path-specific indirect effects. So Nguyen, I think at Hopkins, wrote a paper in the DSEM journal which describes how to do this in Mplus, the binary outcome, binary Y and two mediators. And that's the joint mediator effect, not path specific. And she uses those formulas of expected y star given x and variance of y star given x that I showed you excuse me, earlier. Recently, though, quite recently, actually 2 weeks ago, I saw this article in American Journal of Epi, where they attempt to work with multiple mediators, counterfactual defined effects, and path-specific effects. The most difficult case, the path-specific effect, how much of the indirect effect goes through M1, how much goes through M2. So you may want to read that article. And it looks like it's accessible. With the knowledge that you have from today, I think you should be able to decipher this. I haven't figured out how much of that can be done easily in Mplus yet, but we'll see. Then we have longitudinal mediation and multi-level mediation, which obviously we don't cover here today. We wouldn't have time. Longitudinal mediation, that is, you have x, m, y repeated over many, many time points across time. And some articles to look at and think through is the Maxwell Cole Psychomethods article and the book and Preacher article, structural equation modeling, and a very recent one, 2017, Vanderveel and Tetkin, mediator analysis with time-varying exposures and mediators. So the exposure can vary across time, like I just pointed out, x at different time points. So that's in the JRSSB. That gets a little bit more advanced, but it's okay. Multi-level mediation, that's been written about quite a lot by this team, Chris Preacher and Mike Seifert, and they use Mplus for that multi-level setting. And you see in the Mplus discussion, people keep asking, is this input correct? Is this input correct? So maybe I have to write a chapter on multi-level mediation. It's not too hard. All right, folks, you've been really good. Now it's time for question and answer, and then a break, and then we breeze through the last two topics. Yeah, nothing to it. So who can still ask the most elementary question at this time of the day? Yes, back there. No, I'm pointing to this lady here.
I was just wondering on slide...
Hold on a second, though. Do you know how to turn it on? You have to twist that thing over. Oh, this one. There you go.
On slide.
116. When you have a dichotomous outcome or a non-continuous outcome and a continuous mediator, do you interpret the effects of the predictors on the mediators the same way that you interpret the effects of the mediators on the outcome, like in log odds? So for the TX1 on intent, would it be like the treatment increases the log odds of intent?
No, intent is continuous, so that's a standard linear regression interpretation.
Awesome.
So you don't need to get into log odds there. It's only in the last part of the y on something that you need to get into odds. Yeah, go ahead.
I'll take that basic question to heart there.
That's
Just
good.
can you just define a little bit more about pure and natural and what you meant by those differing terms? I'm not familiar with them.
Okay, so maybe
Do you have it here somewhere in the beginning?
yeah, a little bit further.
97?
Yeah, so that's a good slide, yeah. So what do I mean by natural? Well, that's the idea of M varying as it naturally would in the control group, or M varying as it naturally would in the treatment group. That's where the natural comes in. So it's not a fixed value of M, but it's a natural variation. And that's a big step. There's an alternative where you hold M fixed at certain values, but that's another concept that I'm not going to get into.
So we're not fixing M at a specific value, but at the distribution under condition on a specific value.
And then this is the total natural indirect effect. And a simple way to think of it is that it includes the x times m interaction part. If you exclude it, and I'm talking now in the continuous y, continuous m case for simplicity. If you exclude it, you get the pure natural indirect effect. So to me, I always focus on this. T and I. And T and I plus P and DE add up to the total. So I focus on T and I and P and DE. Those two, that's the only thing I bother with, really. Well, maybe the total too. If you want to exclude the XM interaction, then you look at P9. Does that help? Okay. Next question. Well, I think that lady raised her hand faster.
Thanks. Another very basic question on slide 123. I appreciate the interpretation there, and I noticed the values there. Just to be clear, in order for us to get these values, the output, they're not included in this output. We'd have to go back and generate the output as we did earlier when we were working with the count, because I looked at the output here.
No, this is something that we have
Yeah.
to. We can calculate it in model constraint
Okay.
directly, or just use the output to yeah. So
I just wanted to be sure.
No, we have to do it by hand.
Thank
So,
you.
I mean, so it's an inconvenient way to do it, but it will give us something more easy to interpret, I guess.
And of course, it would be nice to provide that in the output and provide it for more points than the 0 count, but that's not there yet.
Okay.
Yes, now it's your turn, right? If you could pass that down.
So for slide 115,
115.
so you defined the interaction between the intent 4 and treatment 2. So actually there are 3 dummy variables. Why you
Right.
only include 1 and ignore the other 2 dummy variables in the interaction?
So there are 3, if you go to the path diagram, there are 3 TX variables. So we focus on this being 1, and if that's 1, these are 0. So you evaluate effects so they become like C variables, where the effect is defined at them being 0, which is what you want, right? So that one being 1, interacted, multiplied by this intent 4 is the MX.
Yeah, so is
I
it
just did 1 because the author, Sue Hopfer, focused on that specific intervention.
so it's okay to ignore the other dummy variables in creating the
Yeah, if you have a substantive reason for doing that, certainly.
Technically, they're not ignored. They're basically we're working with conditional expectations, and the conditional expectation is conditional on these treatment being 0.
Right, but you don't have TX1 times intent, for instance.
okay.
So you don't have to have all of those interaction terms if you focus on 1.
It's okay to focus on
Yeah.
only one. Yeah, my second question is for slide 106.
Right.
So it seems that it's a group randomization design. So you said the multi-level aspect of the data is ignored. So for what condition can you ignore the multi-level moderate mediation analysis?
You should never ignore the multi-level modeling, multi-level nature, but we can do it. When you want to do an illustration. So this is just a simple illustration. It's not the best way to analyze the data. We didn't want to get into the multi-level version of this. So what it says here is that this is an intervention on the classroom or school level.
Yeah.
So the correct analysis would be a multi-level version of this.
So even if the design effect is very small, you still need to use a multi-level mediation model?
Well, that's a good question for a multi-level training course.
I know it's a little different from this topic,
Right.
but I'm just a little curious.
If you okay, since you're so curious, I would go multi-level. If I were, it's not so much what mistake you make with small design effects, if you ignore them, but what you don't learn. If you do 2-level modeling, you can learn much more. You can learn about effects that vary across clusters, for instance.
You can use type equals complex.
Yeah, and in-between approach would be to use type equals complex to get the right standard errors without having the ambition of estimating parameters of a 2-level model. You estimate a single-level model, but you correct the standard errors. That's type equals complex.
Okay, yeah.
All right.
Thank you.
Okay, we have two questions further back. And we have a microphone here.
In a single level mediation model, in the TE equation, is there a semi-partial correlation or is the semi-partial correlation
Would you
error?
speak into the microphone, please?
So I'm asking if in the single level mediation model, the semi-partial correlation is error in this model, or is it the mediator? Like if you were calculating a semi-partial correlation by hand with 3 circles, 3 latent variables, is the semi-partial correlation the error in TE, or is it M?
Error in TE? What do you mean by that?
Your T.
In intent?
No. In
TX?
getting
In
back
TE
to
as a
this.
total effect?
Yeah, in the total effect.
Okay.
So is it part of the total effect or not? Like, can you map that onto this diagram?
Can I map what?
Can you map 3 circles with a semi-partial correlation that you calculate by hand onto this single level mediation model? Or is the semi-partial correlation error? Or is that the latent residual? Like, what is it?
I don't think I could answer that question. I don't work with
They don't
semi-partial
map.
correlations.
They don't map.
I-
Is that what you're saying?
No, I'm saying I don't know.
You don't know? Okay.
I don't want to commit.
Okay. Just curious.
I don't use
Okay.
those.
Okay.
Further questions in the back? Yes, all right.
Is it okay to ask a question about the morning, or should I not?
No, you can, the whole day, yes.
My question's about slide 59. I think you gave 2 good interpretations in words, but the words that I wrote down opposed one another. So I'm hoping you could just.
I hope I didn't do that. No,
I'm sure it
it's
was me.
difficult. I can, let me see what slide was it? 59. I don't remember the 2 interpretations I did. All right. So as the non-verbal ability, now we have the moderator non-verbal ability to express negative emotions. That was the long definition of that one. Thank you. And that's the moderator here, and we have the indirect effect on the y-axis here. So as this effect increases, as the non-verbal ability to express these negative emotions increase, the negative effect of the dysfunctional behavior mediated by the negative emotions on the work efficiency becomes larger. So it's a larger negative effect. Good thing this is recorded, right? I really hope I got it right.
Otherwise, you can find it in Hayes' book.
Yeah, actually, that's a good reference. And the second way I said it was that for individuals with a high non-verbal ability, it's worse to have, in the sense of in the work efficiency, if you look at the work efficiency, it's worse to have negative emotions about your work. So if you can express them and you have them, that will affect your work efficiency more than if you cannot express them and you have them.
It's his psych background.
Thank you.
I guess.
Okay, next. And where are the microphones? All right,
There's
great.
coming one there from
We'll get to
behind you. There's a mic.
This is a weird question to ask.
I think this lady has the microphone already in hand, so she gets.
I was wondering, when creating the interaction terms for these different models, when is it appropriate to center the terms that you're including in that interaction term? Because I've noticed that for the most part, we're not centering those variables, but then in the last one we did, I think it was the negative binomial one, the inflated one, that we actually did center aggression.
Yeah, I think, so centering before you do an interaction, you don't have to do that. You can, often when you do centering, the interpretations can be easier. And when it comes to, I think that period.
Yeah. I mean, easier in the sense that you can kind of think about what the terms mean, and you can think about that when one is at, and if you look at the equation or the equations there, you can think about that, and one is at the mean, that means that it's 0, so it doesn't affect the whole thing. So you can kind of it's easier to think about what the effect would be at the mean of one part of the moderator. So it's just. I mean, if you can still interpret the moderated model or the interaction effect without centering them in an easy way, then you don't have to do it. So I mean, you should. I think you can turn it around and say, can I interpret this easily? And if I can, well, then I don't have to bother. But if I can't, or if it becomes messy, then maybe I should center it.
There's a good book on interaction in regression analysis by Leona Aiken and Steve West at ASU. But I think Steve West's latest thinking, he commented on this book, so I know, is that all it influences is the interpretation. It doesn't have to be. All right, more questions. Has the microphone reached you? Okay, good.
Just for the parameterization of the model, ultimately,
Yeah.
the results are the same.
Different parameterization, yeah. Right. It doesn't, you're making no mistake.
On slide 154, which is the same one that we looked at 120, but without the moderator.
154?
Yes.
We're not there yet.
I know, but I have a simple question.
Is that really allowed, Bengt?
It's very simple.
Okay, all right.
Okay, I'll bring it up.
It's this. There it is. It's the same one as 120 that included the moderator variable. My question is simply, when you've got aggression at baseline, and then you have aggression 5, which is in between treatment and the long-term outcome, it's almost like measuring the same variable. The aggression 5, do you consider that a change estimate since you've got baseline already predicting the outcome? Like, is that a change score, or is it that variable?
It's that variable. It's not a change score.
Okay.
So it's a variable at 2 different time points. So the person's controlling for his own background.
Okay, so you have the effect of starting level aggression in that bottom. And
Right.
so the amount of variability in aggression 5 that's already explained by aggression 1 is kind of, isn't it removed from aggression 5? So
Well, you could think about that, yeah. Think of it that way.
it looks like we're saying, so I was thinking about the causal nature here.
Mhm.
We're saying for mediation that the treatment affects aggression. So we might see, for example, a reduction, but if you didn't have the aggression 1, you wouldn't know whether aggression 5 was a reduction or was in any way truly related to treatment. That's why I'm just wondering how you think about that, because it looks like that's a change estimate, and I guess that's a better way to do it than doing a pre-post score.
Right. I think of AG1 just as a control variable. It's a randomized situation, and you just strengthen the power to find the treatment effect by including it.
Yeah, but I think you can think in the terms that's a difference in difference or something like that also. I mean, I can see what you mean. But in this case, it's just a control for where everyone starts out. Since it's randomized after aggression 1, yeah, it would be.
No, it's not.
No, it's just temporal order, like in mediation. Like, so we assume that AG1 happened before.
You shouldn't take these examples as totally substantively perfect. They are toy examples that just convey an idea. So don't read too much into them. All right, more questions. We have the microphones. There's one. Yeah, okay.
So I guess the best slide would be 68. It's not a specific slide question, though. I'm wondering, we talked about sensitivity. We talked about looking at rho in the absence of C. We looked at a lot of examples, though, that included C's, and we ignored sensitivity. Is there a reason not to run a sensitivity analysis no matter what?
No, there's no reason to not run that.
Okay.
I think if you want to ever claim causality at all in a mediation model, you should do sensitivity
Right,
analysis.
so regardless of the C's, just run it to make sure there's no unincluded C
Yeah.
that might
Except we only have the sensitivity option in Mplus at this point for the case of continuous M, continuous Y.
Okay.
We haven't gotten to the other cases yet.
But you could do it with a simulation study for certain values.
We include things when we feel a groundswell of need.
But I think that's a very good point. I think you should always, Van der Wele makes that case very strongly too. He thinks that we should kind of make it as a convention or habit to always have sensitivity analysis with these models, because they're so difficult to argue about if you have measured all the confounders or not. So you kind of have to have them. So good point.
No sensitivity for binary outcomes.
Sorry, what?
No options for binary outcomes.
No sensitivity analysis automatically for binary outcomes, no.
But you could do it as a simulation study.